Welcome to Homework Lib.
This problem tells us that the rate of a first-order reaction is followed by spectroscopy, and the absorption is monitored for a color reactant. The reaction occurs in a 1.00 centimeter cell. The only colored species has a molar absorptivity constant of 5.60 times 10 to the third m to the 1 minus molarity of the 1 minus. And that is C, which is the, wait, I lied here. A is the molar absorptivity. Can never spell absorption. Adsorptivity. I think that's right. I hate to spell it wrong on here. Okay, so our first order of business is to calculate the initial concentration. If the absorbance is 0.605, I mean 0.605 at the beginning of the reaction. Okay, that's the first thing we're going to do. We have two other things we're doing. I'll deal with them one at a time. So our initial concentration is going to be equal to the following reaction. C is the molar concentration. A is the molar absorptivity. B is the path length. A and B and A is our absorbance. So let's substitute our values in. 0.605 divided by 5.60 times 10 to the third. Multiply that by our path length, which is 1.00 centimeters. That crosses out, and we get 1.08 times 10 to the minus fourth molar. There's our first calculation. Now let's see what they want us to do for the second part of the problem. B. The absorbance falls to 0.250 in 30 minutes. Calculate the, I got to go to the top of the page. Calculate the rate in units of s to the minus 1. Okay, we're going to use the same as equation as last time to get our concentration here. And this will remain the same. And that will give us a concentration of 4.46 times 10 to the minus fifth molar. And then the integrated weight equation for a first order equation is ln of okay, 30 minutes is 1800 seconds. And our CT, we just calculated, oopsie, is 4.46 times 10 to the minus fifth. And our initial was that we got on the other page was this. And this is going to equal K, negative K, times 1800. So solving for this, K will be equal to 4.9 times 10 to the minus fourth, s to the minus 1. And that is B. For C, we're going to calculate the half-life of the reaction. Okay, half-life for the reaction. I think I have everything I need here. Our half-life will be equal to 0.693 divided by K. And we just solve for K, which equals I'm going to have to punch this one in. I feel like I got a bad answer here. Hang on. I feel like my... I've got 0.693 divided by 4.9 times 10 to the negative fourth equals 1.4 times 10 to the third seconds. Okay, there is C. We have one more part. How long does it take for the absorbance to fall to 1.00? And again, we're going to start with the same equation we started on one. I'll write it down again because it's been a little bit. So C is going to equal 0.100 over 5.60 times 10 to the third that'll equal 1.78 times 10 to the minus fifth molar is our concentration. And we're also going to use this equation. I'll switch colors. Which we've used before. And K we know. So our initial concentration was, whoops, 1.08 times 10 to the minus fourth. Concentration we're dealing with right now is 1.78 times 10 to the minus fifth. That will equal our rate constant, the negative of 4.9 times 10 to the minus fourth. I believe that was s to the minus 1 times our time. Solving for time, we get dang it, I'm going to have to do this one too. We get 3,671 seconds. And that will equal, if I divide that by 60, 61. I better go to 1 sig fig here, maybe 2. 61.2 seconds, or minutes. Or 61 minutes if you want to go to fewer sig figs. Okay. That's it.